So, hello everybody, this is the final presentation of my Capstone project in Advanced Data Science. The title is Detecting Pneumonia with Machine Learning. So the project goal is of course to detect pneumonia, which is lung infection with virus or bacteria. And the best test for pneumonia diagnosis is chest X-ray images. You can see here an example. However, reading X-ray images is not an easy task and requires domain expertise and experience. It would be very helpful if a computer could read the images and recognize the normal and abnormal lungs. So in this project we use deep learning to train and analyze these images and we want to detect pneumonia with it. In the project, I followed the lightweight methodology from IBM Cloud Garage method for data science, which has basically two parts, a process model and an architectural decision guide. So some key points about architectural choices. The data source is provided by Kaggle because it's easy to get, easy to use. And as data repository, I used IBM Cloud Object Store, and also it's easy to use and it integrates best with IBM Watson platform. And for data exploration and integration, I used the Jupyter Notebook with Python 3.5 and Apache Spark 2.3. Main reason for this is that it's easy to realize scalable applications with Apache Spark. As a framework, I use Keras on top of TensorFlow backend, which is an end-to-end open source platform for machine learning, including deep learning. So, as already mentioned, the source data set is from Kaggle. Here is the link. The quality of the images is pretty good because it's already controlled by Kaggle, and all low quality and unreadable scans were removed. The dataset consists, the dataset is pretty small. It only contains about 5,000 images, and it's very unbalanced. So it's 3 times more pneumonia cases than normal cases, which is a challenge for us to train the net. So exactly, it's provided 5,863 X-ray images in JPEG, and it's providing 2 categories, pneumonia and normal ones. It's organized in 3 folders for training, testing, and validation. The images were taken from a medical center in Guangzhou, and they're not fake. They are from they're real images from patients in routine clinical care. And the set for training was has been diagnosis from 2 experts, and they were double checked by a 3rd expert, so we are pretty sure that we provide valid test data. And for next step, extract, transform, load, ETL. Well, we loaded the data set to an IBM Cloud storage for further processing. We could have also used Kaggle API. You can find a link here, which is maybe more sophisticated. The pre-processing is done with Keras image data generator, which doesn't stream but provides batches and also can do some data augmentation. And this makes it very easy to process the data. And basically no data cleansing is necessary because this has already been done prior by Kaggle. Feature creation is normally a big key thing and time consuming in the machine learning workflow, but for deep learning this is really cool because the neural network basically can learn from scratch or from raw data, in this case from raw pixel images, and can recognize complex objects. So feature creation is not a big thing here in our project. So we come to the next step, which is the model definition, which is the core of the project. I try to start with a very simple dense layer network in Keras, but I realized very quickly that the complexity is very high. There are too much parameters to calculate, and so we decided to have a more sophisticated approach, and I used convolutional neural networks, which is specialized for, or can be used very good for analyzing images, and is so widely used in computer vision applications, and that's exactly what we are doing. So this is the central part of my neural network. I skipped a general model definition strategy, which I found helpful for myself. And here are the key points of my model. And this gives me the point to shift to my Jupyter notebook. So here is my Jupyter notebook. And here at the beginning you can see some imports. And basically we start by loading the data from the cloud object storage. Here are the credentials, and we use the IBM library here. We download and unpack the archives, as you can see here. And the next thing is we do visualization, which I have done in another notebook because I had some conflicts with the libraries. Here you can see the images. On the left hand side there are the normal images, and right hand side the one with pneumonia. Going back to the other notebook, we begin basically normal with the pre-processing, but as we use already the input shape from the model, we first of all define the model, and that's basically starting from here. So you can see it's a sequential model, and most of the part are the convolutional 2D layers. We add some max pooling here and here. At one point we flatten the whole thing, add another dense and chop out layer, and finally compile the model here with Adam optimizer. Here I tried another one, and the loss function is categorical cross entropy. Basically here you have the model summary, which says how many parameters you have to calculate, and here the total numbers. And after that we define some callbacks for early stopping if it is not getting better, or what to do if you're on a plateau. They are pretty useful, and I try to experiment a little bit with them. And at this point there's basically the pre-processing with the image data generator, which provides us very conveniently the batches for training, validation and testing, as you can see here. And then we start train the model, and as you can see, with one callback here we reduce the learning rate, and here at epoch 6 the early stopping is triggered. We have defined 10 epochs, but already after 6 we stop because it's not getting better anymore. And so here are the evaluation of our model with the predict generator, and we see the recall precision score and the F1 score, which is a combination of both. And basically I want to show you the confusion matrix, which here you can see the most important one is the false negatives, which is pretty low with 15, because these are the persons the model says they don't have pneumonia, but in fact they have, and this is the worst case. There is a relatively high number of false positive, which are the person the model says they have pneumonia, but in fact they have not. And this is already, I tried other models, and there is a sort of trade-off. If I want to reduce this number, I will get probably some higher numbers on the other square. So here are some other graphs about model accuracy and model loss. But that's the point. I can return back to the slides. So we are back in the slides. We saw how the model was defined. We already saw the confusion matrix and the recall and precision. The recall, which is the best metric for measure for false negatives, is 82%, and we can just provide accuracy because it's not a good metric for imbalanced data set. If you, for example, have 90 negative and 10 positives, having a model with 90% accuracy doesn't tell you anything, because you just could label everything as negative and achieved 90% accuracy. And as already mentioned, we really want to minimize false negative, because this is the most harmful thing when false diagnosing happens. So model deployment is not requirement. There is no requirement here in the project, so just delivered the Jupyter notebook. Well, result recall was already mentioned, and I found it very hard to figure out which parameter to change to improve the model. and also how complex you should model the neural network, how many layers, and so on. It's about experimenting. You start with a simple one, you go more complex and see if it's better. If not, you try the next approach, and so on. Well, one thing which was hard for normal deep learning challenges is the pretty small data set, and also that my processing power was limited, so the model could not be too complex. I really wonder how this could be in real life with a lot of power, with a big data set, how much better the model could be and perform. Well, another thing what I wanted to try is transfer learning, e.g. with a pre-trained model like Inception v3, but well, I didn't have the time on this project. Okay, thank you very much for joining me with this presentation. Have a good time.